Here we're going to take a look at what happens between water molecules in solution. It turns out that water molecules don't just kind of hang around and do nothing in a pure water sample. Some of those water molecules are actually going through changes. And what happens here is that, remember, between two water molecules, we have pretty strong hydrogen bonds that exist. And the constant shifting of those electrons makes it possible for one of the hydrogens from one water molecule to actually bond onto another water molecule. And so what this is referred to as the ionization of water, or because it happens between two water molecules, the auto-ionization of water. And so you can see the products that get formed here. When that hydrogen or that proton is donated from one water molecule to another, you create the hydronium ion. And the hydroxide ion. And again, this is referred to as the auto-ionization of water. Now, what's not really clear in this picture is that these species, the hydronium ion and the hydroxide ion, don't stay that way. If these two ions happen to bump into each other at some point in the solution, there's a good likelihood that they would go back in the other direction. And yeah, proton would get donated back to the hydroxide from the hydronium, and you would end up with two water molecules again. And so this process continuously goes back and forth between the two molecules on the left and the ion and the molecule on the right. Now, the extent to which this happens is basically 1 in 10 million molecules of water, or two molecules, I guess, out of 10 million water molecules will do this in any one time, in a particular time. But it is a dynamic process that does go back and forth. The other thing that's important for us to keep in mind here is our kind of our acid-base idea. And because the water molecule on the left is accepting a proton, that is the Bronsted-Lowry definition of a base. And the water molecule on the right is donating the proton, so that would be the Bronsted-Lowry definition of an acid. So here we see that water is both acting as a base and an acid. The term we use to describe that is amphoteric. So a substance that can act as both an acid and a base is referred to as amphoteric. And again, you notice that we form conjugate acid-base pairs. So from the water on the left, we accept a proton, and so that base becomes an acid over here. Right, so that would be the conjugate acid-base pair. And the water molecule on the right, which is losing the proton, would be paired up with the hydroxide ion, which would be the base on the left. So that would be another conjugate acid-base pair. What we want to do now is take a look at this equilibrium in a little more depth. So let's rewrite this again. So we've got H2O plus H2O going in both directions to H3O plus OH minus. So again, it's an equilibrium. This is an equilibrium situation, which means that it goes back and forth. Well, this equilibrium is kind of like a teeter-totter. You reach a balancing point, and then it doesn't stop. It keeps going back and forth, but it stays balanced. What that produces is what's called an ion product constant. And this is kind of an important idea in equilibrium because it allows us to quantify equilibrium a little bit. And in the case of water, what this means is that if I take at any given time, if I take the concentration of the hydronium ion and I multiply that times the concentration of the hydroxide ion, that product is equal to a constant. In this case, we're going to call that constant the Kw for water. So K being the constant and W meaning for water. And for water at 25 degrees Celsius, the value of the Kw is 1 times 10 to the negative 14th. So it means that at any time, the product of the concentration of those two ions has to equal 1 times 10 to the minus 14th. So for instance, if I knew that my hydronium concentration was equal to, let's say 1 times 10 to the minus 4th molar, and I wanted to find out the concentration of the OH minus, I could rearrange my equation and say, all right, well, the concentration of the hydroxide ion would be equal to my Kw divided by the concentration of the hydronium ion. And we would have 1 times 10 to the minus 14th divided by 1 times 10 to the minus 4th. And that would give us 1 times 10 to the minus 10th for the OH minus concentration. So you can see that, if you knew either one of those concentrations, you can figure out the other one. So it's kind of an important idea there. The other thing that we're going to take a look at is, whether a solution would be considered acidic or basic. So let's take a quick look at how that would work out. So if it's neutral, that's probably the easiest way to start out. If it's neutral, the H plus concentration has to equal the OH minus concentration. Right, so that would be neutral. Well, we know that the product of those two things has to equal the Kw, which is our 1 times 10 to the minus 14th. Right? So what that means then is if those two are equal, then we can set those equal, make that equal to x. And we can say then that the Kw would be equal to x squared. And so x, if we plug in our values or take the square root of the Kw, x would be 1 times 10 to the minus 7th molar. So at a molarity of 1 times 10 to the minus 7th, for H plus and OH minus, we would have a neutral solution. So let's put that down here. H plus equals OH minus equals 1 times 10 to the minus 7th molar. So what this means then is that for something to be acidic, we need to have more hydrogen ion than hydroxide ion. So the H plus concentration would have to be greater than the OH minus concentration, and that would make it acidic. If it was basic, that would mean that the H plus concentration would be less than the OH minus concentration. So, and in the next video, we'll take a look at the pH scale, which is the quantitative scale that we use to measure the acidity and basicity of a solution.